Hello students, welcome to video lesson 6-6. In this lesson we're going to be talking about two more special types of quadrilaterals or four-sided shapes, but these are not parallelograms. Okay, in our last few videos, since we started talking about parallelograms, everything that we've dealt with has been parallelograms: rhombuses, rectangles, squares, etc. In this video, we're going to talk about two special quadrilaterals that are not parallelograms, okay? And the first one is a trapezoid. A trapezoid, I think, is a shape that we have some familiarity with. It is a quadrilateral with one pair of parallel sides. Okay, that's different than a parallelogram because a parallelogram had both pairs of sides parallel, right? In a trapezoid, we only have one, okay? So we can't have a trapezoid and a parallelogram at the same time. Okay, trapezoid is only one pair of parallel sides. Now those parallel sides, which I have here shown with these purple arrows, these parallel sides are called the bases of the trapezoid. So a trapezoid has two bases. Okay, we're maybe sort of used to seeing the base of a triangle or maybe even the base and height of a rectangle. In a trapezoid we have two bases. So we call one of them base 1, we call the other one base 2. And it doesn't really matter which one's 1 and 2, but there are two bases, okay? Those are the parallel sides. The parallel sides of a trapezoid are called bases. The non-parallel sides of a trapezoid, okay, the ones that are not parallel, are called legs. So there's a leg here and there's a leg here, okay? So we have two bases, we have two legs. That makes up the four sides of our trapezoid, all right? So two bases, two legs. The properties that we're going to look at today, for the most part, well, the first two, are about a special kind of trapezoid, which is called an isosceles trapezoid. Okay, and if we have some understanding of what an isosceles triangle is, which we should because we talked about those in chapter 4, isosceles triangles, remember, two side lengths the same. Isosceles trapezoid has, again, two side lengths the same. But it's a very specific two sides, okay? An isosceles trapezoid is a trapezoid with congruent legs. So that means this leg is congruent to this leg over here, okay? The legs are congruent. The bases can't be congruent, you guys, because if they were, then we actually had a fancy theorem back in section 6-3 that said if I have a four-sided shape and one pair of sides are parallel and congruent, then it's a parallelogram. So because this is a trapezoid, it can't be the bases. The bases can't be congruent in a trapezoid, okay? But the legs can be congruent, in which case we have what we call an isosceles trapezoid, okay? And our first two properties today are about specifically isosceles trapezoids, okay? Not all trapezoids, but specifically isosceles trapezoids. Then we'll look at one property or characteristic of all trapezoids. But we're going to start with two properties of isosceles trapezoids, okay? And these, the first one is found on page 389 in your book, and the second one at the top of page 391. So the first property, which I call isostrap property number 1, okay, because this is specifically about isosceles trapezoids, remember? Isosceles trapezoid property number 1 is that similar to isosceles triangles, all the base angles are congruent, okay? So remember when we had isosceles triangles, if I just draw us one real quick right here, okay, when we had isosceles triangles, when we knew that this side and this side were the same, we also knew that the angles across from them were the same, right? That was our isosceles triangle theorem back in chapter 4. So it's the same idea in trapezoids. If we have an isosceles trapezoid, then both pairs of the angles along the same base are congruent to each other, okay? So what I mean is this. If I have this leg is the same as this leg, then across from that leg and across from this leg, those angles have to be the same, okay, across that bottom base. Those angles in the corners on that bottom base have to be congruent because of the isosceles trapezoid, okay? And then the same is true if we go to the other base. If we go up here, okay, on the top base, those angles on the top also have to be the same, okay? Now, it's important to recognize that you might see a trapezoid in your book or sometime that is not positioned where the longer base is on the bottom and the shorter base is on the top. It might be turned slightly, okay? So we have to be okay with seeing trapezoids tipped and turned and twisted a little bit. But each pair of base angles in an isosceles trapezoid is always congruent, similar to what we saw with triangles back in chapter 4, okay? So that's property number 1. In an isosceles trapezoid, base angles are congruent, both pairs, 2 pairs of angles that are congruent, okay? Isosceles trapezoid property number 2 is actually the same as the only property of rectangles that we looked at, okay? So isosceles trapezoid property number 2 says that the diagonals of an isosceles trapezoid are congruent to each other, okay, the length of them. So the distance from A to C is congruent to the distance from D to B, okay? These diagonals have to be congruent if you have an isosceles trapezoid, okay, a specific kind of trapezoid, then we have congruent diagonals, okay? Now, remember that this is not a parallelogram, so the diagonals do not cut each other into 2 equal pieces, right, which should make sense because the distance from A to that point seems longer than the distance from C to that point, and it absolutely is, okay? So the diagonals do not get cut into 2 equal pieces, but the whole diagonal length is congruent in an isosceles trapezoid, okay? A to C and B to D. These are congruent. All right, so there's our 2 properties of isosceles trapezoids. Isosceles trapezoid property 1, isosceles trapezoid property number 2. I'm not going to ask you to prove these, but they are homework problems where we're asked to prove them, but we're not actually going to do that, okay? So the question is, what are we going to have to do with the properties? Well, similar to just about everything we've done so far in this chapter, we're going to either be finding missing angles or potentially doing algebra, okay? Potentially doing algebra. So here we have an isosceles trapezoid, CDEF, and we're given one angle measure. We're given this angle measure, 65 degrees down here. Okay, they want us to find the measure of all the other 3 angles. Okay, all other 3 angles. Well, the easiest one to find for us should be the one that we know is the same as angle C, because this is an isosceles trapezoid. And which one has to be the same as angle C? Well, it's the base angle with angle C, right? So if it's not angle C, it must be along the parallel side, must be angle F. Okay, so the measure of angle F has to be 65 degrees as well. Okay, now we know that D and E are also going to be the same. The question is, how many degrees are they going to be? There's actually 2 ways to figure this out and 2 ways to think about it. Number 1, we can remember back to section 6.1 where we were talking about the sum of the interior angles of polygons, right? And we had that formula n minus 2 multiplied by 180 degrees. So if you do that with a 4-sided shape, a 4-sided shape's interior angles always add up to be 360 degrees. Okay, it's always 360 for these 4 angles inside a 4-sided shape, which should make sense, right? Because rectangles and squares have 4 angles and they're all what? 90 degrees, right? 4 times 90 is 360. So if we know that these have to add up to be 360, and we know that the bottom 2 are both 65, 65 plus another 65, well, that makes 130. So how much is left for these top 2 angles? Well, 360 minus 130 would be 230, I think. Right? So this is what the top 2 angles together have to equal, 230 degrees, okay, to make 360 total. And then if I just divide it by 2, that should give me each one, right? Because I know they have to be the same. So 230 divided by 2 is 115 degrees. So the measure of angle D, please do write your answers like this. You guys, when you're asked to find the measures of angles, I want to see measure angle this guy, okay? If you can name the angle in that way. is 115, and then we know measure of angle E is the same. Measure angle E is also 115. Okay? So that's one way to do this. The other way to do this is actually not to think about polygons as much as we think about parallel lines. Okay, so if we think all the way back to chapter 2 or 3, whenever it was we were talking about parallel lines and alternate interior angles and so on and so on and so on like that. If I extend some of these sides, we should see some parallel lines and some transversals. Okay, and then if I extend the transversal. Okay, remember, I'm trying to find this angle up here, right? This is the angle that I want to find right there. So if I look at that red starred angle and this 65-degree angle, what kind of angles are they in this picture? Well, they're on the same side of my transversal and they're between the two parallel sides. So those are same side interior angles. Okay, now if we remember back to same side interior angles, those were the only ones that we ever looked at that weren't congruent when we had pictures like this, right? They weren't congruent, but they were supplementary. So they have to add up to 180 degrees. Okay, so by the way, that's always going to be true in every trapezoid ever, that the two angles along a leg, meaning a not parallel side, a slanty side, the two angles along a leg are always going to be supplementary, okay, meaning add up to 180, and it's because of the same side interior angles theorem. So if we know this is 65, if we did 180 minus 65, what would we get? Well, we'd get 115. Okay, so maybe you think that's an easier way to do it, is just know that this way they're going to be equal along the bases, and then along the legs they're going to be supplementary or add up to 180 degrees. Okay, either way we can find these angles just given one angle in a trapezoid. In an isosceles trapezoid we can find the other three. Okay, so we're going to skip over that one. Now, the other thing that we're going to have to do with trapezoids today is a property or characteristic, as I mentioned, that applies to all trapezoids. Okay, so now we can expand and broaden our minds to include all trapezoids. So even something that looked, you know, like something that looked like this. Okay, that is a trapezoid, but it's not an isosceles trapezoid, because the legs here and here are not congruent to each other, but this side is parallel to this side, right? So this is a trapezoid, just not an isosceles trapezoid. So now we need to expand our minds to all trapezoids, okay? And they have this thing called a mid-segment, all right? And a mid-segment of a trapezoid is the segment that connects the midpoints of the legs. Okay, so if I were to mark off the midpoints of these two legs, let's say, okay, the midpoint of this leg is maybe right about there, and the midpoint of this leg is maybe right about there. Okay, those are the two midpoints of the legs. Like that cuts this into two equal pieces. Whoopsies. Cuts this into two equal pieces, and then it also cuts this one over here, cuts this one into two equal pieces. So these are the mid segments, okay? They're the bisectors, if you will, of these legs. If I draw a segment or draw a line between these two, okay, between these two mid segments, or excuse me, midpoints, okay, between the two midpoints, this is something called a mid segment, all right? So in between the two midpoints is called a mid segment. It's the segment that connects the midpoints of the two legs. Okay, that is the mid segment of a trapezoid. And then there's something special about the mid segment. In fact, there's two special things about the mid segment. One, maybe you can pick up on just from looking at the picture. Okay, one special thing about the mid segment, which is part of theorem 621, the trapezoid mid segment theorem, is that the mid segment of every trapezoid ever is parallel to both of the bases. Okay, so it's basically a third segment that's parallel to the two bases. So now you have three going across that are all parallel. Okay, so in this case, this is parallel to this, and it's parallel to this. Okay, all three of those lines, they're all parallel. All right, so that's characteristic number one of the mid-segment of a trapezoid. Got to be parallel. Okay, that also, by the way, gives you a bunch of congruent angles because of like corresponding angles and things like that. So that tells me those two angles are the same as these two angles. Okay, or sorry, these two angles are the same as each other, not necessarily the same altogether. Okay, but there's a bunch of congruent angles in here. The second thing that's true about mid-segments of a trapezoid is that the mid-segment, this distance from this side all the way over to this side, is half as much as the two bases added together. Okay, the mid-segment length is half as much as the two bases added together. All right. A different way to put that actually makes the algebra that we're asked to do a lot easier is this. If you double the mid-segment length, you take the mid-segment length and you double it, it equals the two bases added together. Okay, if you double the mid-segment, so 2 times the mid-segment length, it's equal to the two bases added together. All right, so those are the two things that we know about trapezoid mid-segments from the trapezoid mid-segment theorem. What you're going to have to do with that in your practice problems is algebra. Okay, so we're going to look at something like this. So here we have a picture, and we're being asked to find the value of x given this picture, that this is a trapezoid and QR is our mid-segment. So this is our mid-segment, and we're asked to find the value of x in this picture, okay? So what I want you to remember is if we double the mid-segment length, it should equal the two bases added together. So let's think first about, okay, if I double the mid-segment, if I double the mid-segment, what is that going to look like? Well, right now the mid-segment is x plus 2. So what's twice as much as x plus 2? Well, 2 times x plus 2, if you like the distributive property from algebra class, right? Distribute the 2. I think I get 2x plus 4. So this is what I get when I double the mid-segment. I do 2 times the mid-segment, I get 2x plus 4. And remember what that has to equal. That is supposed to equal the two bases added together. Well, what are the two bases added together? Well, the two bases are 4x minus 10 and 8, right? So if I take those and I add them together, what am I going to get? 4x minus 10 plus 8. Well, minus 10 plus 8 is going to make a minus 2, right? So what I end up with is 4x minus 2. And now I know these have to be equal because one of them is 2 times the mid-segment and the other one is the two bases added together. And those two things have to always be equal. So I can do algebra here, right? I can move things around and I can solve for x. I would add 2 here and I would add 2 over here to the 4 and I would minus the 2 x's and I would minus these 2 x's and I get 2x is equal to 6. So x would need to equal 3. Okay, so I think x is equal to 3. How can I check my answer though? How can I make sure that x is equal to 3? Well, I can plug x back into the picture, right? So if I plug x equals 3 into here, I think I get that the mid-segment is 5. Okay, so remember, that's supposed to be half as much as the two bases added together. So what do the two bases added together then need to be? Well, if 5 is supposed to be half as much, it should be 10. So if I put 3 into this top part, 4 times 3 is 12. 12 minus 10 makes 2. So that's 2. The other base is 8. What do you get when you do 2 plus 8? You get 10. 2 plus 8 is 10. Cut that in half, you get 5, right? So I got it right. It came out perfect in my picture, okay? 2 plus 8 is 10. You cut it in half, you get 5. So we can do algebra. We can find missing lengths, okay, of mid-segments. We can also find missing base lengths if we just put an X on there and then do some algebra, right? Okay, so That's all about trapezoids, okay? That's it for trapezoids. The other thing in section 6.6, the other special quadrilateral is something called a kite, all right? So we're gonna look at a couple things about kites, and then that's gonna be the end of this section. So a kite is sort of like a rhombus, but it's not the same, okay? A kite is a quadrilateral with both pairs of consecutive sides congruent. Now remember, consecutive means right next to each other, right? So if I were to draw a kite, here's what I need to do. I make two sides that are right next to each other that are the same length. Okay, so those are the same length, and then I make two more sides going this way that are also the same length. Okay, so that's a kite, where this side is the same length as this side, and then this side here is the same length as this side here. All right, so two pairs of sides that are congruent, but those sides are consecutive. They share a vertex or a corner, okay? They're not opposite across the shape from each other. They're actually right next to each other, all right? So I have two congruent sides here and two congruent sides here, all right? Now, the reason I said kites are sort of like rhombuses is because their property that we're gonna look at is the same as the rhombus property. I think it was rhombus property number 1. And rhombus property number 1, and in this case, what we'll call kite property number 1, even though we only have one of them, is that the diagonals of the kite are perpendicular. Okay, they have to meet at 90 degrees. So here's another example of a kite, and they've drawn the two diagonals, AC this way and BD going this way. Okay, AC and BD, they have to meet at a 90-degree angle. Okay, that's what makes a kite. Right? Now, there are more things that we can know about kites that are going to be more helpful for us in what we're asked to do in our practice problems, but this is the only like theorem property that we have for kites in this section, okay? But another thing I want you to write down about kites is that the diagonals of a kite create 3 sets of congruent triangles, okay? So I've drawn them for you here. Okay, when I have both diagonals, I have red triangles on this side that are congruent to each other. I have blue triangles here that are congruent to each other, okay? And it's not super hard to prove them congruent. We just sort of use hypotenuse leg for these ones, okay? Because they share all this stuff. But then also if you just draw the one diagonal that goes from the corner with this pair of congruent sides to the corner with this pair of congruent sides, if you draw that diagonal, you slice the shape into 2 big triangles that are also congruent, okay, and they're congruent by side, side, side because we have those congruent and these congruent, and then of course down the middle we have that side that's the same as itself, so that's side, side, side. Okay, so using these congruent triangles, then we should realize that there are a lot of congruent angles in this kite as well, especially once we draw our diagonals, okay? So for example, this angle has to be the same as this angle down here, and then this angle in the blue triangles has to be the same as this angle in the blue triangles, and then these angles here have to be congruent, and then these angles over here also have to be congruent. Okay, so that horizontal diagonal, the one that goes this way in a kite that's shaped like this, cuts angle A and angle C in half. Okay, that's another property of that diagonal. So using all of this information about congruent triangles and perpendicular diagonals, we're going to be asked to find measures of angles. Okay, so in this particular picture, we're asked to find 3 angle measures, right? Angle 1, 2, and 3. If I start with the measure of angle 1, that should be the easiest one because I want you to recognize where angle 1 is in the picture. Right? Where is angle 1 in the picture? Well, it's at the meeting point of the diagonals, right? And we know that in a kite, okay, is a kite. So it is a kite. What do we know about the diagonals? Well, they have to meet at a 90-degree angle. Okay, they have to meet at a 90-degree angle. What about the measure of angle 2? Well, if we're gonna find the measure of angle 2, I'm gonna need to take out a triangle from the picture. Okay, so this is point D up here, and I know this is a 90-degree angle. I know that this angle right here is marked for me as 52 degrees, right? That angle is 52 degrees. That's what they show me right here. So if that angle is 52 degrees, then what is this angle down here? Well, remember that the three angles in a triangle always have to add up to 180. So if I know this one is 90 and I know this one is 52, can I find that one? Yes, I can. I can just do 180 minus 90 minus 52. Okay, and you're going to come out to 38 degrees. So the measure of angle 2 is 38 degrees. Okay, and now the measure of angle 3. Well, the measure of angle 3 is in the other triangle, right? Is in the other triangle that's congruent to the one I was just dealing with, right? Because we know this side is the same as this side. We know this is 90-degree angle, and they share this side. So they're congruent triangles right here. So this 52-degree angle and angle 3 are in corresponding positions, right? And what do we know about corresponding parts of congruent triangles? They're congruent. So angle 3 is 52 degrees. Okay, so we're using the idea of congruent triangles. We're using the idea of 90-degree angles and angles that we know to find missing angles in a kite. All right. If you have any questions about trapezoids, kites, or their properties, or what you're being asked to do in your practice problems, please do reach out to me. I am available all the time. Email, phone, Zoom office hours are all good ways to get a hold of me. If not, that's all I have for you, and we will talk to you soon.